So this is Neurophysiology Notes number 2, so let's go over diffusion. So it's driven by three properties: the concentration differences, valence of the ion, and voltage difference across the membrane. So concentration differences is just, for example, if there's a higher concentration of sodium outside the cell than inside. Valence of the ion is talking about, for example, sodium is a +1 charge, and then calcium is, for example, 2+ charge. And then the voltage difference across the membrane helps you know that, helps you understand that there will be a greater diffusion, for example, if there's a greater voltage difference. So to talk more about these concentration differences, let's look at the general ion concentrations in a cell, specifically mammal neurons, right? So you don't have to memorize these exact numbers because these numbers obviously fluctuate depending on the neuron, depending on the animal. But just know the general numbers, and you can also know the general concentrations, right? So, for example, sodium, there's generally a higher concentration outside the cell than inside. And then for potassium, there's a higher concentration inside the cell than outside. Calcium, there's a higher concentration inside the cell than outside the cell than inside. And then chloride, a higher concentration outside the cell than inside. And this is just a random piece of knowledge, but the reason why there's only a small amount of calcium inside the cell is because calcium acts as a signaling molecule. So obviously you don't want to have a lot of calcium inside if you're using it as a signaling molecule. So moving on, let's talk about the Nernst potential, right? So what is the Nernst potential? And just to let you know, the Nernst potential is the same as the reversal potential. And for a single ion system, reversal and equilibrium potential are the same. So if we're just talking about one ion, equilibrium, reversal, and Nernst are all the same thing, and they can be used interchangeably. And so what is it? It's the dynamic equilibrium between concentration and electrical gradients, right? So in general, concentrations of ions that are high outside the cell will want to go inside, so you'll have that going on. But there's also the electrical gradient of, for example, sodium is a plus charge wanting to go inside the cell because there's negative charges. So just to show you an example, you have, and this is talking about the third piece, right? Which is the voltage difference across the membrane. So when you have -70 millivolts, right, that's a huge potential difference. So the amount of ion influx will be very large, right? So see how the arrow is bigger here than here? Well, that's what it's trying to show. The bigger the potential difference, the higher the current, right? But over here, the arrow starts getting a little bit smaller at -20 millivolts. And then especially at +60 millivolts, when sodium is approaching its equilibrium or Nernst potential or reversal potential, the arrows start getting smaller, right? And on top of that, they start going in and out because it has reached a dynamic equilibrium between concentration and electrical gradient. So at this point, it's going in because of the concentration gradients, but then starts slowing down because it's starting to reach its Nernst potential. And at this point, when it reaches +60, there's a dynamic equilibrium right here. So moving on, the equilibrium potential. So once again, the equilibrium potential is just where the net ion flux is equal. So it doesn't mean that there's no ion flow. It means that the ion flow inside and outside is equal to 0. Or there's still ions moving in and out, just at the same rate. So there's no net ion flux, the key word being net. So what is the Nernst equation? So we have two of them, right? So we have voltage is equal to RT/ZF ln over C outside and C inside, right? To go over all these terms, V is the Nernst or equilibrium potential. Remember that volts is equal to potential. C equals concentration of the outside, right? Concentration of the outside ions, concentration of the inside ions. R is the gas constant, T is the temperature, F is Faraday's constant, and Z is the charge of the ion. And over here, it's the same equation. It's just that they replaced ln with 2.3 and log. In general, the most important parts of this equation, because I think they'll give you most of these, it's not like you have to memorize these constants, at least if your teacher's nice, I guess. But the most important part is the z part, because that's the charge of the ion. So that's what will really change. All these others are constants, right? And then obviously the outside and inside concentrations that you'll plug in. But z, that's the trick part, because for example, for most cases it'll be normal. It'll just be 1, right? Because for example, sodium, potassium, they're all +1. But if you have calcium, then it would be 2, right? And that suddenly changes it. And I'll show you what it does. So this, in most cases, they'll be nice and they'll simplify it at 37 degrees to become this equation. V equals 61.5 log over concentration outside over concentration inside. So that's the case, right? But for, like I said, what about calcium 2 plus? So in this case, Z equals the charge of the ion. So for Z, you'd put 2, right? So what does that do? If you think about it, well, if you put 2 here, that's the same as 1/2, right? Because it's 1 over the 2. So it would just be 1/2 times this. So it'd actually be 61.5 divided by 2. So then it would just be this entire equation, but just divided in half, right? So that's the only trick with the Nernst equation that they could throw at you during exams. So moving on, we have the resting membrane potential. So it's dependent on 2 things. It's dependent on the separation of charge and the permeability of the membrane to the ions. So what does that mean? Well, for example, the sodium-potassium pump creates a separation charge, right? It creates this imbalance to help when you have an action potential. And the permeability of the membrane to the ions, well, you know from general neuroscience that there's a larger amount of leaky potassium channels, which means that there's a larger amount of ion channels that are free to move potassium in and out of the cell at will, meaning it's not closed at rest. And though that means that the entire resting membrane potential is dependent on potassium. So this is further explored in the Goldman-Hodgkin-Katz equation. So you can see it looks a little more complicated than the Nernst equation, but in reality it uses the same constants. And the difference of the Nernst equation is that it includes permeabilities of each ion. See how it has P in here? So P of the permeability of sodium and the permeability of potassium. So what this does is it can show you how the entire membrane potential is affected when you change the permeability of different ions. And that's what I was talking about when the difference in the, for example, the large number of leaky potassium channels, right? Because since you have a large number of them, the entire resting membrane potential becomes dependent on potassium. So, for example, if you work at the math, the relative permeability at rest for potassium is 40, while the relative permeability at sodium is just 1. So that means the resting membrane potential is dependent on K plus potassium, potassium's Nernst potential. So it shows that the relative membrane potential is larger for potassium because of the larger amount of leaky potassium ion channels. So moving on, this is the key part about learning neurophysiology. What I feel is the most important part. Because the neuron can be looked at as a parallel circuit, and so you can make a lot of references to it. And it is a parallel circuit. And so the first thing to talk about in reference to a neuron is Ohm's law. So for example, you have this little circuit going on, and you have the voltage, right? Voltage is just the potential difference. You have the R, resistance, and I is current, right? So you have positive and negative. And so now you can look at a neuron as the case of a parallel circuit. I know this is a series circuit, but you can look at it as a parallel circuit. So, for example, the concentration difference in ions causes the potential difference and thus represents the battery of the cell. So you have a bunch of ions, for example, sodium once again, right? The concentration difference of the sodium ions causes a potential difference, and so you can view the neuron in the neuron, the battery, as the ions themselves. Because what do the ions do? They cause the potential difference, and that's what the battery does in a circuit. It causes the potential difference. And so for the neuron, the membrane itself is a capacitor, and the ion channels, they act as resistors to ion flow, right? Because if the ion channels are closed, that means that the ions can't get in, and therefore they act as resistors. So once again, the neuron can be viewed as a parallel circuit. And so adding more resistors, right, adding more ion channels will reduce overall resistance. So this is an important concept to understand, because it'll likely be on a test, for example. They'll ask, if you added more sodium channels, what happens to the overall resistance? So let's talk about the physics part of this. So you have the parallel equation for resistance, right, which is 1 over total resistance is equal to 1 over the first resistor, 1 over the second resistor, and so on, right? So let's say the resistance of one of these resistors is 2, right? So if you have one ion channel, it would be 1 over RT is equal to 1 over 2, right? Because we would just plug in that 2 for that one ion channel. Now, the quickest way to solve this is just to flip both sides, but I wanted to show you the math version to make sure that you understand why we can just flip it and just say RT is equal to 2. Just multiply each side by RT. These cancel out, so it just become 1. Over here, it become R2 divided by 2, and then multiply each side by 2, and then these two will cancel out, and then you would get 2 is equal to RT. The quicker version is just to flip them, and then you have your answer. RT equals 2. Over here, right, so we got that for this system, total resistance is equal to 2. So, for example, if the question asked, what happens if we added one more sodium channel, how would that affect overall resistance? So we have 1 over RT is equal to 1 over 2, right, because we just randomly decided that R is equal to 2 for one ion channel. So 1 over 2 plus a 1 over 2. So since we're adding, right, 1 over 2 plus 1 over 2 is 1, and then is equal to 1 over RT. And I already proved over here that we can just flip it. So RT equals 1. So notice how when we added another ion channel, the total resistance actually decreased, because over here it's 1, but when we only had one ion channel, it was 2. So I hope that proves the point, and then therefore on an exam, you can get this question right, that when you add more ion channels, the overall resistance decreases. So, and let's talk about the final thing, which is the membrane acts as a capacitor. So the cell membrane is a capacitor, because if you look at the definition of a capacitor is two conductors, and the two conductors in our neuron are the solution inside and outside the cell, separated by an insulator. The insulator is the membrane itself, right? So the cell membranes in general have a capacitance of 1 UF, F is farads, which is the units of capacitance, over centimeters squared. And the equation for capacitance is C equals 2 constants and area divided by diameter. So, or distance. So the thing about this is you don't have to worry about these two values, because that's not the important here. The importance, for example, on a question is how does distance affect the capacitance? So, for example, if you had a distance of 4 here, right, and you had a distance of 2 here, I try to draw it here to appear smaller. But for example, if you had d over here and d equals 4 here and d equals 2 over here, and let's assume a equals 1, right? The area is the same for both. A equals 1. So over here, you'd have capacitance is equal to 1, right? Which is the area, which we assume for both, and then divided by the distance. So d equals 4 over here. So we have 4. So for this one, it's C equals, the capacitance is 1 over 4. Over here, if we have 2, we can add in the distance into the formula, and so it becomes C equals 1 over 2. Notice how when the distance decreases, the capacitance increases, because 1/2 is bigger than 1 over 4. Therefore, the main takeaway I want you to take away from this is just know that as you decrease the distance, you actually increase the capacitance. And I think that should make a little bit of sense, right? Because if you have two charges or here and here, obviously the strength is going to be there. It's going to be more connected to each other when they're closer together, right? Because they can, for example, if you have two magnets, the strength of the magnets will increase as you bring the magnets closer together. So I hope that helped, and thanks for watching.